In the last two videos, we started to talk about finding the limit at infinity of rational functions, functions where the numerator and the denominator are both polynomials. In the last two videos, we looked at really simple cases where the numerator was a constant and where the denominator was a constant. So they weren't changing at all. And then the other part was approaching infinity. And so what we noticed was that when the numerator is approaching infinity and the denominator is constant, the limit is always equal to infinity. And then we saw when we flipped it over that when the numerator is staying constant and the denominator is growing and growing and growing, that fraction is approaching zero. Okay, and that matches, I think that matches our intuition that when you've got a fraction, if the numerator is getting bigger and bigger and bigger and the denominator is standing the same, the value of the fraction is increasing. And if the numerator is staying the same and the denominator is getting bigger and bigger and bigger, then the value of the fraction is still positive, but getting smaller. And so that means that the limit is going to approach zero. What we're going to do now is we're going to look at more complicated functions where we've got both the numerator and the denominator changing. And so we're going to see how that changes the situation. All right. So let's take a look at the function that we looked at when we were doing graphs and talking about horizontal and vertical asymptotes. And so that was the function 3x plus 1 over x minus 2. All right, and once again, I'm going to solve this without a graphing calculator this time. I'm going to solve it without a spreadsheet, and I'm going to solve it without even using a normal calculator. I'm going to make a table for this case, but in general, you're not even going to make a table. All right, so first of all, let's put in 10. So if I substitute 10 in for this, I get 3x plus 1. 30 plus 1 is going to be 31 over 10 minus 2 is 9. All right, if I put in 100, I'm going to get that's 300 plus 1 is 301 divided by 100 minus 2 is 98. I said 9 there. I meant 8, didn't I? And let's do a big jump. Let's put in 1,000,000. All right, so this is just going to stand in for our really huge number. So 3 times 1,000,000 plus 1 is equal to 3,000,001 divided by 1,000,000 minus 2 is 999,998. All right, now let's try figuring out how big this number is. And again, we can't use a calculator. So when I've got a problem like that and I can't use a calculator, I want to do a little estimating. All right, so let's, instead of using these weird numbers, why don't we use more round numbers? So what's an easy number to deal with that's easier to deal with than 3,000,000 plus 1, but is still close to 3,000,000 plus 1? I heard somebody say 3,000,000. Excellent choice. Why don't I even just write that in words? 3,000,000. All right. And 999,998, that's a complicated number. Can I round that to a number that's easier to deal with? Yeah, why don't I call that 1,000,000? All right, so this fraction is almost exactly 3,000,000 divided by 1,000,000. And what's that equal to? Well, we can just cancel out our millions, can't we? And that gives us 3. All right, as the numbers get larger and larger, as our x values get larger and larger, we're going to have numbers here in our numerator and denominator that are increasingly close to 3 times each other. Because the thing that is keeping this from being 3,000,000 and the thing that's keeping this from being 1,000,000 is this positive 1 and this negative 2. And as 3x and x get bigger and bigger and bigger, that 1 and that negative 2 are going to be more and more and more insignificant. So what I'm going to do is I'm going to say that this function, 3x plus 1 over x minus 2, is Asymptotically equal, I'm using just, it's kind of like an approximation with two tilde marks. You don't need to worry about that symbol at all. But that's just about 3x over x. I'm taking out the 1 and the -2 because those are insignificant as my x values are getting larger and larger and larger. And 3x over x, I've got an x in the numerator and x in the denominator. I can cancel those out. That's something that I'm allowed to do in algebra as long as x isn't equal to 0. And I know that x isn't equal to 0 because x is a very large number when I'm thinking about this limit. This is a number that is close to infinity. So that is approximately equal to the limit as x approaches infinity of 3. And we didn't talk about the limits of constant things, but this constant function, no matter what x is, the value of this is going to be equal to 3. All right, so that is a way, so we just took this complicated function and we turned it into a function where we could use one of our three rules and just say that the answer was equal to 3. Let's take another example of this. Let's say that we have the limit as x approaches infinity of 5x minus 4 over 9x plus 7. All right, give that a quick shot and see if you can solve that. Pause the video if you need to. I'm going to do it without even using the table this time, because I'm going to do the same thought that we did before, that this 5x minus 4, as x gets bigger and bigger and bigger, this -4 becomes more and more insignificant, so I can forget about it. Again, this +7 is going to be more and more insignificant as x gets bigger and bigger and bigger. When x is 1, that's 9 plus 7 is 16. That's a really big difference from just the 9. But if x is 1,000,000, this is 9,000,007. Okay, and so the amount of that is taken away by just forgetting about that 7 is so small we don't need to bother about it. So we've got 5x over 9x. We can just cancel out the 5 and the 9. I'm sorry, we cancel out the x's, and that leaves us 5 over 9 as our limit. And what you can do if you want to do is you can hop over to GeoGebra and graph that function, 5x minus 4 over 9x plus 7, and see that as x approaches infinity, you'd need to draw the line where x is equal to 5/9, y is equal to 5/9, excuse me. But you would see that that is the asymptote of that function. All right, so that is one step of our functions where we're thinking about the limits at infinity of rational functions.